Welcome friends to this lecture on linear algebra for the competitive examinations. Myself, Mr. S.M. Chinchola, Assistant Professor in Mathematics, MG Vidyamandir, Science and Commerce College, Manmad. The syllabus for various competitive examinations on linear algebra contain the topics: vector spaces, subspaces, linear independence, dependence, basis, dimension, algebra of linear transformations, then algebra of matrices, rank and determinant of matrices, linear equations, then eigenvalues and eigenvectors, Cayley-Hamilton theorem, matrix representation of linear transformation, change of basis, canonical forms, diagonal forms, triangular forms, Jordan forms, inner product spaces, orthonormal bases, quadratic forms, then reduction and classification of quadratic forms. Generally, for the NET examination, there is a part A containing multiple choice questions. There are 40 multiple choice questions, out of which a candidate shall be required to answer any 25 questions. Each question shall be of 3 marks and the total marks allotted to this section shall be 75 out of 200 marks. Out of these 40 questions, there are 7 to 8 questions on linear algebra. We are going to start the questions. Let N be the non-empty subset of a vector space such that A is a subset of B. Then if B is linearly independent, then so is A. If B is linearly dependent, then so is A. Third option is if A is linearly independent, then so is B. And fourth option is if B is generating set, then so is A. The correct option is if B is linearly independent, then so is A. If B is linearly independent, then so is A. And the explanation for this is that the subset of linearly independent set is linearly independent. A is a subset of B. So if B is linearly independent, A is also linearly independent, while the superset of linearly dependent set is linearly dependent. That means if A is linearly dependent, then B should be linearly dependent. But our option was if A is linearly independent, then B is linearly independent. It is not true. Also, if B is linearly dependent, then A need not be linearly dependent. So the option 2, second and third are wrong. And next remark is a superset of spanning set, that means generating set, is also a spanning or generating set. And subset of spanning set or generating set need not be a spanning or generating set. Therefore the option 4 that says if B is generating set, then so is A, it is wrong, because subset of generating set need not be a generating. Subset of dependent set need not be a dependent set. Okay. Superset of independent set need not be independent. So options B, C and D are wrong. And the correct option is A. Subset of linearly independent set is linearly independent. So if B is linearly independent, A is also linearly independent. Second question is, let T from R2 to R2 be the linear transformation defined by T of xy is equal to x comma x plus y. Then the matrix of T with respect to the standard basis is, first option is 2 by 2 matrix column wise 1 0 0 1. Second option is 2 by 2 matrix column wise 1 1 0 0. Third option is 2 by 2 matrix column wise 1 1 0 1. And fourth option is 2 by 2 matrix column wise 0 1 0 1. We know that the standard basis for R2 contains the vectors E1 vector is equal to 1 0 and E2 vector is equal to 0 1. Here the correct option is option C. The 2 by 2 matrix column wise 1 1 0 1. The explanation is, as we know that the standard basis for the R2 contains the vectors E1 vector is equal to 1 0 and E2 vector is equal to 0 1. To get the matrix of transformation, first of all you have to find the images of that standard basis vectors of domain. Okay, the images of standard basis vectors of domain under the given transformation. Domain is R2, its standard basis vectors are E1 vector is equal to 1 0, E2 vector is equal to 0 1. So we have to find their images under the transformation T of xy is equal to x plus y. So T of E1 vector is equal to T of 1 0. To get T of 1 0, you have to substitute x is equal to 1 and y is equal to 0 in this transformation. So we get T of 1 0 is equal to 1 comma 1 plus 0. That means 1 1. Now you have to express this image 1 1 as a linear combination of basis vectors of codomain. Here codomain is again R2 and it also have a standard basis. E1 vector is equal to 1 0, E2 vector is equal to 0 1. So you have to express this 1 1 as a linear combination of 1 0 and 0 1. So it can be written as 1 1 is equal to 1 0 plus 0 1. Again, this 1 0 is nothing but E1 vector, this 0 1 is nothing but E2 vector, so it will be 1 times E1 vector plus 1 times E2 vector. See here, this E1 vector is nothing but the standard basis for domain, and these E1, E2 vectors are the standard basis vectors of codomain. Okay. Now you have to take the second standard basis vector of domain and find its image under the given transformation. That means T of E2 vector is equal to T of 0 1. You have to substitute x is equal to 0, y is equal to 1 in this transformation. So you will get is equal to 0 comma 0 plus 1. It is equal to 0 1. Now you have to express it as a linear combination of standard basis vectors of codomain. That means you have to express it as a linear combination of 1 0 and 0 1. So it can be written as 0 times 1 0 plus 1 times 0 1. This 1 0 is nothing but again E1 vector, 0 1 is E2 vector. So we will get T of E2 vector is equal to 0 times E1 vector, 1 times E2 vector. Means we express now the images of basis vectors of images of basis vectors of domain as a linear combination of basis vectors of codomain. We have expressed here the images of basis vectors of domain under the linear transformation as a linear combination of basis vectors of codomain. Now you have to write their coefficients, means the coefficients in the linear combination column wise to get the matrix of transformation. That means you have to write this first coefficient in the first linear combination 1 as the first element of first column, and this second coefficient as the second element of first column. Again, from the second linear combination, you have to write this first coefficient as the first element of second column, and second element as the second coefficient as the second element of second column, and you will get this matrix of transformations 2 by 2 matrix, column wise 1 1 0 1. Third question is, let A be an m by n real matrix, then the space of solution satisfying linear system x is equal to 0 has a dimension. First option is A m, second option is at most minimum of m and n, third option is at least m minus n, and fourth option is at least n minus m. The correct answer is D, at least n minus m. We know the rank nullity theorem for the matrices. Rank plus nullity of matrix is equal to the number of columns of that matrix. Here the number of columns of A is n, so we will get rank plus nullity of A is equal to n. Again, we know that the rank of matrix is nothing but the number of non-zero rows in its row echelon form. So the rank of matrix cannot exceed the number of rows of that matrix. So rank of A should be less than or equal to its number of rows, that is m. So rank of A is less than or equal to m. Rank less equal m. So minus rank is greater than or equal to minus m. We know that when we multiply any inequality by negative number, its inequality sign changes. Now, as rank of A plus nullity of A is equal to n, we can say nullity of A is equal to n minus rank of A. But this minus rank is greater or equal minus m. Minus rank is greater or equal minus m. So you have to replace this minus rank by greater or equal minus m. So we will get nullity is greater than or equal to n minus m. Nullity of matrix A is nothing but the dimension of null space of A, which is nothing but the dimension of solution space of linear system x is equal to 0. Note that the solution space of homogeneous linear system x is equal to 0 is nothing but the null space of matrix A. So the dimension of solution space of x is equal to 0 is nothing but the dimension of null space of A, that means nullity of A. And we get nullity of A is greater than or equal to n minus m, means it is at least n minus m. So we get the result that this linear system x is equal to 0, The solution space of this linear system x is equal to 0 has dimension at least n minus m, which is nothing but the nullity of A, or dimension of null space of A. Fourth question is, let A be an n by n matrix over set of real numbers R such that the rows of A form orthonormal basis of Rn. Then first option is the columns of A are linearly dependent. Second option, the rows of A are linearly dependent. Third option is A is singular. Fourth option is the columns of A form an orthonormal basis of Rn. The correct option is fourth. The columns of A form an orthonormal basis of Rn. The explanation is, when the rows of A form an orthonormal basis of Rn, then A is orthogonal matrix. A is orthogonal matrix, therefore its transpose A transpose is also orthogonal matrix. As A transpose is orthogonal matrix, its rows also form an orthonormal basis of Rn. And rows of A transpose are nothing but the columns of A. So we will get the result, columns of A form an orthonormal basis of Rn. Okay. Fifth question is, let A and B be similar matrices. Then first option is rank A is equal to rank B, but the nullity of A need not be the same as the nullity of B. Second option is rank A is equal to rank B and nullity of A is equal to nullity of B. Third option is the nullity of A need not be the same as the nullity of B, and rank A need not be the same as rank B. And fourth option is nullity of A is equal to nullity of B, but the rank A need not be the same as rank B. And the correct option is correct option is B, that is rank A is equal to rank B and nullity of A is equal to nullity of B. As A and B are similar matrices, there exists an invertible matrix P such that A is equal to P inverse BP. As A and B are similar matrices, there exists invertible matrix P such that A is equal to P inverse BP. A is equal to P inverse BP. So what we get? Rank of A is equal to rank of B. Rank of A is equal to rank of B. And as A and B are similar matrices, that means A is equal to P inverse BP, where P and P inverse are the square matrices of same order. So the orders of A and B are also same. A and B are of same order. Now what we get? Rank of A is equal to rank of B, and order of A is equal to order of B. But by rank nullity theorem, rank plus nullity of matrix is equal to number of columns of that matrix. So rank of A plus nullity of A is equal to number of columns of A. Similarly, rank of B plus nullity of B is equal to number of columns of B. But number of columns of A and number of columns of B are same. Rank of A and rank of B are same. So we conclude that nullity of A is also equal to nullity of B. So we will get the conclusion, rank A is equal to rank B and nullity of A is equal to nullity of B. Sixth question is, which of the following is the basis for the vector space satisfying polynomials in Rx of degree less than or equal to 3? First option is 1 plus x square, 4 minus x, 11 plus x square plus 4x cube. Second option is 1, 3 plus x square plus x cube, 4 plus x plus 2x square plus 2x cube. Third option is x cube plus x square plus x plus 1, x cube plus x square plus 3x plus 1. And fourth option is 3, 4 minus x, 2 plus 3x plus x square plus x cube, 4 plus 7x plus x cube. See the vector space for the polynomials in Rx of degree less equal 3. That means it is P3. We know that the dimension of vector space of polynomials in Rx of degree less equal 3. That means dimension of P3 is 4. Dimension of P3 is 4. So its any basis should contain exactly 4 vectors. And here the correct option is D. The vectors in the basis of P3 are 3, 4 minus x, 2 plus 3x plus x square plus x cube, 4 plus 7x plus x cube. The explanation is, in the first option, degree of P3x is 4. Degree of P3x is 4, but the vectors given in the option A are only 3. 1 plus x plus x square, 4 minus x, 11 plus x plus x square plus 4x cube. It contains only 3 vectors, so it cannot form a basis for P3. For B, we have given 4 vectors, but among that 4 vectors, 1 can be expressed as a linear combination of remaining 3. That means fourth vector in the option B, 4 plus x plus 2x square plus 2x cube, can be expressed as a linear combination of first 3, that means 1 times 1 plus 1 times 3 plus x plus 2 times x square plus x cube. Therefore, these 4 vectors are linearly dependent vectors, and we know that basis vectors are always linearly independent. Here we get the vectors in option B as linearly dependent, so they cannot form a basis for P3. Again, similar reason for option C. We have given 4 vectors, but fourth vector x cube plus x square plus 3x plus 1 can be expressed as a linear combination of first 3, that is x cube plus x square plus x plus x plus 1. So they are linearly dependent and cannot form a basis for P3. So the correct option is D. Here, if we write these 4 vectors in the linear combination and equate it is equal to 0, a times 3 plus b times 4 minus x plus a times 2 plus 3x plus x square plus x cube plus b times 4 plus 7x plus x cube is equal to 0. Then you will get 3 into a plus 4 times b plus 2 times c plus 4 times d, that is constant term, 3a plus 4b plus 2c plus 4d, plus coefficients of x as minus b plus 3c plus 7d times x plus coefficient of x square, that is c into 1 plus nothing, that means c times x square, plus coefficient of x cube as c times x cube, that means c plus d times x, that is dc plus d times x cube is equal to 0. So this linear combination is equal to 0 if and only if all the coefficients are is equal to 0. That means we will get 3a plus 4b plus 2c plus 4d is equal to 0, minus b plus 3c plus 7d is equal to 0, c is equal to 0, c plus d is equal to 0. As c is equal to 0, when we substitute c is equal to 0, you will get d is also is equal to 0. When we substitute c is equal to d is equal to 0 in the third relation, we will get b is equal to 0. And when we substitute b is equal to c is equal to d is equal to 0 in the first relation, we will get a is equal to 0. So this linear combination is equal to 0 if and only if all the coefficients are 0. This implies that these 4 vectors given in the option D are linearly independent. And as we have 4 vectors in P3 which are linearly independent and the dimension of P3 is 4, this linearly independent set automatically form a basis for P3. Seventh question is, let x and y be similar matrices. Which of the following statements is not true? First option is x and y have the same eigenvalues. Second option is x and y have the same characteristic polynomials. Third option is x and y have the same nullity. Fourth option is x and y have the same eigenvectors. As already I have told you, when we have two similar matrices, their rank and nullity are also same, so the option C is correct, but we want the incorrect statement. So the incorrect statement is statement D, that is x and y have the same eigenvectors. The explanation is, when A and B are similar matrices, then they have same determinant. Determinant of similar matrices is, and determinants of similar matrices are equal. They have same trace. Trace is nothing but the sum of the diagonal entries of square matrix. Okay, so they have same trace. They have same rank. I have already told you. They have same nullity also. They have same characteristic polynomial. So they have same eigenvalues also, and have same number of eigenvectors. Same number of independent eigenvectors. But actual eigenvectors may be different. Okay, same number of independent eigenvectors, but probably not the same eigenvectors. Okay, same number of independent eigenvectors, but that eigenvectors need not be same. So the option D, that x and y have same eigenvectors, is incorrect, not true. Next question is, the characteristic equation of a matrix is x cube minus 2x square minus x plus 1 is equal to 0 if lambda 1, lambda 2, lambda 3 are eigenvalues of the matrix. Then lambda 1 square plus lambda 2 square plus lambda 3 square is equal to, option A is 3, option B is 5, option C is 6, option D is 8. See, as we have the characteristic equation x cube minus 2x square minus x plus 1 is equal to 0, and lambda 1, lambda 2, lambda 3 are eigenvalues of that matrix. These eigenvalues are the roots of characteristic equation x cube minus 2x square minus x plus 1 is equal to 0. So the correct option is option C, that is 6, and explanation C here. As lambda 1, lambda 2, lambda 3 are the eigenvalues, these are the roots of characteristic equation, that is x cube minus 2x square minus x plus 1 is equal to 0. Okay, and this equation is actually monic equation, cubic monic equation. So lambda 1, lambda 2, lambda 3 becomes the roots of monic cubic equation, and we know the relations between the roots and coefficients of a monic polynomial equation. So we get the sum of the roots is equal to minus coefficient of x raised to n minus 1. So lambda 1 plus lambda 2 plus lambda 3 is equal to minus coefficient of x square, that means minus of minus 2. So we will get lambda 1 plus lambda 2 plus lambda 3 is equal to minus of minus 2, that is plus 2. Again, the sum of the product of pairs of roots, the sum of the product of pairs of roots, distinct pairs of roots, is equal to the coefficient of x raised to n minus 2. That means here lambda 1 into lambda 2 plus lambda 1 into lambda 3 plus lambda 2 into lambda 3 is equal to coefficient of ax, that will be minus 1. Okay, now what we want? We want lambda 1 square plus lambda 2 square plus lambda 3 square. How we can express this? We know that lambda 1 plus lambda 2 plus lambda 3 bracket square is equal to lambda 1 square plus lambda 2 square plus lambda 3 square plus 2 times lambda 1 lambda 2 plus 2 times lambda 1 lambda 3 plus 2 times lambda 2 lambda 3. Okay, so we get lambda 1 square plus lambda 2 square lambda plus lambda 3 square is equal to lambda 1 plus lambda 2 plus lambda 3 bracket square minus that 2 times lambda 1 lambda 2 plus lambda 1 lambda 3 plus lambda 2 lambda 3. So we will get the value of lambda 1 square plus lambda 2 square plus lambda 3 square by substituting here the values of lambda 1 plus lambda 2 plus lambda 3 is equal to plus 2, and lambda 1 into lambda 2 plus lambda 2 into lambda 3 plus lambda 1 lambda 3 is equal to minus 1. We will get it is equal to 2 square minus 2 times minus 1, that means 4 plus 2, that is equal to 6. So the correct option is C, that is 6. Next question is, let v1 vector, v2 vector, v3 vector dot 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 vn vector be eigenvectors corresponding to the eigenvalues c1, c2, cn respectively of a linear transformation. Then which of the following is true? First option is, if v1, v2, v3, vn are distinct, then c1, c2, cn are also distinct. If c1, c2, cn are distinct, then v1, v2, vn are linearly independent. If v1, v2, vn are linearly independent, then c1, c2, cn are distinct. The vectors v1, v2, vn are linearly independent if and only if c1, c2, cn are distinct. The correct option is option B, that is if c1, c2, cn are distinct, means if eigenvalues are distinct, the eigenvectors are linearly independent. If c1, c2, cn are distinct, then v1, v2, vn are linearly independent. The explanation is, suppose v1, v2, v3, vn are non-zero eigenvectors of a matrix A belonging to distinct eigenvalues c1, c2, cn, then v1, v2, vn are linearly independent. Okay, so when c1, c2, cn are distinct, the corresponding eigenvectors are linearly independent. An identity matrix, we know that identity matrix have n equal eigenvalues, all equals to 1, but still it have n linearly independent eigenvector, that is 1 0 0 0 0 1 0 0 0 0 0 0 0 0 1 dot dot 0, that means standard basis 0 0 0 dot 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 1, standard basis of Rn. Okay, identity matrix have n equal eigenvalues, but it has n linearly independent eigenvectors. So when we have independent eigenvectors, it need not imply the eigenvalues are distinct. Okay. Next question is, let W be a subspace of the Euclidean space E, then W is equal to W orthogonal, W is equal to orthogonal of W orthogonal, C orthogonal of W orthogonal is a proper subset of W, and D is W in an orthogonal of W orthogonal is equal to singleton 0. D is not correct, it is just by observation. Okay. A is also not correct because every subspace cannot be equal to its orthogonal. So there is only possibility among B and C. C. Option D is correct. W is equal to orthogonal of W orthogonal. What is the explanation? Let W be a subspace of the Euclidean space E, then W orthogonal is also a subspace of E. And what is the property? W direct sum W orthogonal is equal to E. That means if we take union of W and W orthogonal, we will get the E, and when if we take intersection of W and W orthogonal, there is only a zero vector. Means W union W orthogonal is equal to E, and W intersection W orthogonal is equal to singleton zero vector. Now this happens for W orthogonal also. Means the orthogonal of W orthogonal is also a subspace of E, and W orthogonal direction orthogonal of W orthogonal is equal to E. That means W orthogonal union orthogonal of W orthogonal is equal to E, and W orthogonal intersection with orthogonal of W orthogonal is equal to singleton zero vector. If we observe these two statements, then you can conclude that W and W double orthogonal, means orthogonal of W orthogonal, both have same elements. So we will get W is equal to orthogonal of W orthogonal. Next question, which of the following matrices is diagonalizable? Option A is 3 by 3 matrix, column wise 5 0 0 6 8 0 7 9 10. Option B is column wise 1 1 0 1 2 by 2 matrix. Option C is column wise 0 0 1 0 2 by 2 matrix. Option D is 3 by 3 matrix, column wise 1 0 0 0 2 0 0 1 2. The correct option is A, that is 3 by 3 matrix, column wise 5 0 0 6 8 0 7 9 10. What is the explanation? Being upper triangular matrix, the eigenvalues of the matrix in the option A are C1 is equal to 5, C2 is equal to 8, C3 is equal to 10. And by calculation, the eigenvectors corresponding to C1, C2, C3 are V1 vector is equal to 1 0 0, V2 vector is equal to 2 1 0, V3 vector is equal to, here should be V3, V3 vector is equal to 34 by 5, 9 by 2, 1. And these are linearly independent eigenvectors. Okay, so we get the, as these eigenvectors are linearly independent, we have the matrix P which is invertible. Here P is equal to 1 0 0, 2 1 0, 34 by 5, 9 by 2, 1 from the independent eigenvectors, and we get its inverse as it is invertible, such that A is equal to PA P inverse. So this concludes that A is diagonalizable. This concludes that A is diagonalizable. While for the option D, being upper triangular matrix, the eigenvalues of matrix in D is equal to 1 1 0 1 are again C1 is equal to 1, C2 is equal to 1. Okay, C1 is equal to 1, C2 is equal to 1. So we get the corresponding eigenvectors as V1 vector is equal to 0 1 for first eigenvalue, and V2 vector is equal to again 0 1 for the second eigenvalue. So these two eigenvectors are one and the same, so they are linearly dependent, not linearly independent, and hence B is not diagonalizable. Option C have upper triangular matrix and so its eigenvalues are again C1 is equal to 0, C2 is equal to 0, and so the corresponding eigenvectors are also same, that is 1 0 1 0, which are not linearly independent. So this matrix is also not diagonalizable. In the option D, again it is a upper triangular matrix, so the eigenvalues of this matrix are C1 is equal to 1, C2 is equal to 2, C3 is equal to 2, and the corresponding eigenvectors you can find them as v1 vector is equal to 1 0 0, v2 is equal to 0 1 0, v3 is equal to 0 1 0. Again this v2 vector and v3 vector are same, so these eigenvectors are linearly dependent, not linearly independent, so it cannot be diagonalizable. Next question is, let A be Hermitian matrix, then determinant A is a real number, A is positive definite, A is unitary, A is symmetric. The correct option is option A, determinant A is a real number. See the explanation. The matrix A is equal to Aij of complex entries is said to be Hermitian if and only if the conjugate of its transpose is equal to that matrix itself. Conjugate of transpose is equal to that matrix itself. So what we get, Aij is equal to conjugate of Aji, means Aii is equal to conjugate of Aii. It happens only when Aii is a real number, means the diagonal entries of this matrix are real numbers, and diagonal elements of A are real numbers, and the elements on opposite sides of main diagonal are conjugates of each other, means A12 is conjugate of A21, A23 is conjugate of A32, A31 is conjugate of A13, in this way. Okay, so determinant A becomes a real number, because when you are going to find determinant in most of the terms, the products are of the form Aij, Aji, and as they are conjugates of each other, they are converted into the real entries, and the all remaining are cancelled. Okay, so determinant A becomes real number. 13th question is, let V of F is a vector space over a field F. Consider the following statements. If alpha, beta, gamma are linearly independent vectors in V at F, then alpha plus beta, beta plus gamma, gamma plus alpha are also linearly independent. The set of vectors A, subset of V over F, which contains the zero vector, is always linearly independent. Then options are both first and second are true, both first and second are false, only first is true, only second is true. Obviously second is not true, because we know that every set of vectors containing zero vector is always linearly dependent. Okay, so first and fourth option cannot be correct. So there is only chance for answers as option B or option C, and the correct option is option C. That means only one is true. That means if alpha, beta are linearly independent vectors in V over F, then alpha plus beta, beta plus gamma, gamma plus alpha are also linearly independent. See the explanation. If we express this alpha plus beta, beta plus gamma, gamma plus alpha as a linear combination equal to zero vector, then we get x times alpha plus beta plus y times beta plus gamma plus z times gamma plus alpha is equal to 0. By taking similar vectors together, we will get x plus z times alpha vector plus x plus y times beta vector plus y plus z times gamma vector is equal to 0 vector. But already we have given alpha, beta, gamma are linearly independent. As they are linearly independent, their linear combination is equal to 0 vector if and only if each and every coefficient in that linear combination is equal to 0. So we will get x plus z is equal to 0, x plus y is equal to 0, y plus z is equal to 0. By solving these three equations, we will get x is equal to y is equal to z is equal to 0. That means whenever we take linear combination of alpha plus beta, beta plus gamma, gamma plus alpha, and equate it to 0, we get all the coefficients is equal to 0. This shows that alpha plus beta, beta plus gamma, gamma plus alpha, these three vectors are also linearly independent. So the first statement is true and second is obviously false. Every subset of a vector space containing a zero vector is linearly dependent, cannot be linearly independent. So second is false, first is only true. So the option is C. For change questions, let f from R3 to R3 be defined by f of x, y, z is equal to 2x plus y minus z, x minus y, x plus z, where the basis of the domain is the usual basis, that means standard basis, and that of the codomain is 1, 1, 1, 1, 1, 0, 1, 0, 0. Then the matrix of f relative to these bases is, first option is 3 by 3 matrix, column wise 1, 0, 1, 0 minus 1 minus 1, 1, 2 minus 1. Second option is 3 by 3 matrix, column wise 1, 3, 2, 2, 2, 1, 3, 1, 3. Third option is 3 by 3 matrix, column wise 1, 0, 1, 0 minus 1, 2, 1 minus 1 minus 1. Fourth option is 3 by 3 matrix, column wise 1, 0, 0, 0, 1, 0, 0, 0, 1. And the correct option is option C, 3 by 3 matrix, column wise 1, 0, 1, 0 minus 1, 2, 1 minus 1 minus 1. As already we have taken one of the similar example. Here we have the usual basis for domain, that means standard basis for domain, that is e1 vector is equal to 1, 0, 0, e2 vector is equal to 0, 0, 1, 0, and e3 vector is equal to 0, 0, 1. To find the matrix of transformation, what we have to take? We have to take its images, the images of basis vectors of R3. That means e1 vector, e2 vector, e3 vector under the given transformation. So we have to first of all find f of e1 vector, that means f of 1, 0, 0, by substituting x is equal to 1, y is equal to z is equal to 0, as f of e1 vector is equal to 2, 1, 1. We get f of e1 vector is equal to 2, 1, 1. Now we have to express this image 2, 1, 1 as a linear combination of basis vectors of codomain. But we are given basis vectors for codomain as 1, 1, 1, 1, 1, 0, 1, 0, 0. This 2, 1, 1 can be expressed as 1 times 1, 1, 1 plus 1 times 1, 0, 0 plus 0 times 1, 1, 0. So it will be 1 times 1, 1, 1 plus 0 times 1, 1, 0 plus 1 times 1, 0, 0. These 1, 1, 1, 1, 1, 0, 1, 0, 0 are the basis vectors of codomain. Now we have to express f of e2 vector. F of e2 vector is equal to f of 0, 1, 0. We have to substitute x is equal to z is equal to 0 and y is equal to 1. So we will get image as 1 minus 1, 0. Now you have to express this 1 minus 1, 0 again as a linear combination of basis vectors of codomain. So we will get it as 0 times 1, 1, 1 plus minus 1 times 1, 1, 0 plus 2 times 1, 0, 0. Now we have to express third basis vector, e3 vector is equal to 0, 0, 1. You have to find its image under the given transformation. By substituting x is equal to y is equal to 0 and z is equal to 1, you will get image as minus 1, 0, plus 1. Okay, and it can be expressed as a linear combination of basis vectors of codomain as 1 times 1, 1, 1 plus minus 1 times 1, 1, 0 plus minus 1 times 1, 0, 0. Okay, so the matrix of transformation can be obtained by writing the coefficients in the linear combinations column wise. That means first column of that matrix of transformation will be 1, 0, 1. Second column of that matrix of transformation will be 0, minus 1, 2. And third column of that matrix of transformation will be 1, minus 1, minus 1. So the correct option is C. Then the matrix of F relative to the basis is matrix in the option C. Next question, which of the following functions t from R2 to R2 is not a linear transformation? First option is t of AB is equal to A plus B, comma A minus B. Second option is t of AB is equal to A plus B, comma B. Third option is t of AB is equal to 1 plus A, comma B. Fourth option is t of AB is equal to BA. As we know that whenever we are going to observe the linear transformation of the vector, general vector in the domain, the components in the images should be the linear combination of that two vectors, okay. That means here the correct option, that means the transformation which is not linear is t of AB is equal to 1 plus A, comma B, because 1 plus A is not a linear combination of A and B. Vector of The explanation is this component of TAB should be of the form as a linear combination of A and B, that means X plus By. Then and then that will be the linear transformation, otherwise it cannot be linear transformation. So the correct option is C, where obviously X and Y are real numbers. Next question, let V be a vector space over a field F and T from V to V be a linear transformation such that T has 0 as a characteristic root. T has 0 as a characteristic root. Then first option is that T is diagonalizable over F. Second option is multiplicity of each characteristic root of T is 1. Third option is T is invertible, and fourth option is T is nilpotent. The correct option is A, T is diagonalizable over F. C, the explanation. 0 is the eigenvalue of T if and only if T is singular. And T is singular if and only if T is not invertible, and so if and only if it is not injective. Okay, means T is not invertible. T from R2 to R2 defined by T of xy is equal to x plus 2y, 3x plus 6y is such that T of minus 2, 1, T of minus 2, 1 is equal to, when we substitute here x is equal to minus 1, x is equal to minus 2, y is equal to 1, we will get here 0 and here again 0. So it will be 0 times minus 2, 1. That means 0 is an eigenvalue of T. But T is not linear transformation. If you take any power of T, you cannot get the 0 transformation. So it is not linear, it is not nilpotent transformation. If T from R to R2 is defined by T of xy is equal to x plus y 0, then we have T of minus 1, 1 is equal to 0, 0. That means 0 times minus 1, 1. We show that 0 is an eigenvalue of T. And T minus I bracket square of 1, 0 is equal to T minus I operating on 1 plus 0 minus 1, comma 0 minus 0 is equal to 0, 0. Okay, that is 1 is the characteristic root with multiplicity 2. Okay, 1 is the characteristic root with multiplicity 2. Means if 0 is the characteristic root of linear transformation, then T need not be invertible, T need not be nilpotent transformation, and there is no conclusion that 1 is not the characteristic root with, there is no characteristic root with multiplicity 2. The correct option is A, that is T is diagonalizable over F. 17th question, let F from U to V be a linear map and U1 vector, U2 vector, Un vector be the set of linearly independent vectors in U. Then the set of vectors means images of vectors in this linearly independent set, that is f of u1 vector, f of u2 vector, f of un vector is linearly independent if and only. Means what? The image set of linearly independent set is also linearly independent if and only if first option is f is 1 1 and 1 2, second option is f is 1 1, third option is f is 1 2, and fourth option is u is equal to v. There is no need to get u is equal to v. There is no need to the function to be on 2. The only necessity for the image set of linearly independent set under the linear transformation is linearly independent if and only that linear transformation is injective, that means 1 1. So the correct option is f is 1 1. 18th question is let A is equal to 3 by 4 matrix with column wise 1 1 1 1 2 4 0 1 0 0 0 1 be a matrix of transformation, then the rank of A equal to. So the you can find the rank of A by reducing it in the row echelon form or any other method. The options are A2, B3, C4, D1. As A have 3 rows, its rank cannot exceed 3. So the option C is not correct. and the correct option is B, that is 3. How can we get the conclusion 3? As I have already told you, you can reduce it in the row echelon form and check it. Otherwise, we have another option. It has sub-matrix 1 2 4 0 1 0 0 0 1 of order 3 by 3. Its determinant is not equal to 0. Its determinant is 1, not equal to 0. Why its determinant is 1? Because it is lower triangular matrix. When we have a lower triangular matrix, its determinant is nothing but the product of diagonal entries, that is equal to 1. As A have submatrix of order 3 by 3 having non-zero determinants, its rank will be greater than or equal to 3. Again, as it has only 3 rows, its rank cannot be exceed 3. So the rank of A is equal to 3, and the correct option is B. Next question, let S is equal to U1 vector, U2 vector, UP vector be linearly independent subset of a vector space V is equal to vector space spanned by vectors V1 vector, V2 vector, VQ vector. Then this set is a linearly independent subset of vector space V containing P vectors, and V is spanned by Q number of vectors V1 vector, V2 vector, VQ vector. Then first option is P is less than Q, second option is P is equal to Q, third option is P less equal Q, and fourth option is P greater than Q. And the correct option is option C, that is P less than or equal to Q. Because we have the basis for the, as V is spanned by the vectors V1 vector, V2 vector, VQ vector, this V1 vector, V2 vector, VQ vector forms a basis for V. So the every superset of these basis of vector space is linearly dependent. Means every set containing more than Q vectors is linearly dependent. So every linearly independent set can have at most Q vectors, and as S contains P vectors which is linearly independent, this P is at most equals to Q, means it is always less than or equal to Q. A vector space V has a basis V1 vector, V2 vector, VQ vector, its dimension is Q. Any set of vectors in a vector space having vectors more than dimension is always linearly dependent. As it is linearly independent, its value is less than or equal to Q. Next question is, if T from R3 to R3 is identity map, then nullity of T is equal to, option A is 0, option B is 1, option C is 2, option D is 3. Correct option is option A, that is 0. Because T is a linear, T is the identity map, its matrix of transformation is 1 0 0 0 1 0 0 0 1. Its rank is 3 and nullity is 0. Similarly, we get the kernel of T as vector containing only 0 vector 0 0 0. So its dimension